This is mathheals.com, where you can find more links to math and computer science YouTube videos. And let's take a look at an introduction to functions of several variables. And the first thing talks about determine whether something's a function or not when you're talking about several variables. And should have had that cleaned off. But let me get a tablet going up here. Now remember, when we had functions of, or we just had f of x is equal to 3x minus y. We had x over here, and then we had this function notation over here that was the same as y. Well, we're going to see something similar to that in this section. And these first ones actually just determine whether z is a function of x and y. And not that I could probably graph it, but if we had a sphere, for example, looking at a 3D picture like that, what this is asking us to determine for two variables, we had for every x there's only one y. So we're going to have a different definition here. I'm going to put this in terms of x's and y's, but you can even have more than that. For every point, x, y, there is only one z. So there is only one z. Of course, if you had x, y, and z here, then you could throw another variable in there. If I look at this 3D, remember with our axis here, I have that right there. And if I looked at the sphere, this is my z-axis. Well, for a particular point, if I pick it in the middle of the sphere, then this one would fail because there'd be two different x, y values that would give me the same z value. There'd be one over on this side, and there'd be one over on this side. For all three of these points, your z value would be the same because your z is up and down. But over here, this x would be, well, if I put it exactly in the middle there, x would be 0. But y would be something. This is your x-axis, remember, and this is your y-axis. So y might be negative 3, and over here y might be positive 3. So there's two different x values, or x, y values that give us that z value. So pretending that this point over here is 0, negative 3, just in terms of my x values, then those would also give me the same z value. Let's say it's 0. As 0, 3, 0. This one over here. Again, these are x and y, and you see how the z values are the same here. Now that's what that definition is saying. And if you got the graph, a lot of times you can look at it and you can see it. And it's a very hard one to work with if you don't have the graph. Sometimes you can just spot it. But we had a definition for determining if something's a function in college algebra, and we'll modify that. It's a little bit easier definition, and it doesn't work all the time, but kind of gives us some place to start. It says if you have one of the following, it is not a function. And we're talking specifically where you're just dealing with 3 dimensions, x, y, and z. This is not. So if you have a z squared, z to the 4th, or z to an even power, it's not a function. If you have the absolute value of z, then it's not a function. If you got a plus or minus, and this one's a little bit tricky, but you got a plus or minus on the other side. Now this plus or minus, depending upon what else is with it, may not what you think on that. And then certain planes will cause us problems too. Let's look at this first one here. We got x z to the fourth plus natural log of x minus xy is equal to 3. We said we can't have a z to the fourth power, didn't we? So this is, and the instructions say determine whether z is a function of x and y. So this one's not a function. Second problem. We have x squared y plus xyz minus y is equal to 0. Now by looking at this, we only have one z, or wait a minute, I wrote that down wrong. Jeez, I'm blind. Mr. Magoo. See, we have z to the first, and we have z to the first. Well, that's not z to an even power, so this would be a function. Now again, this won't work all the time, but just kind of give us a kind of a starting place. Sometimes you just have to think about it, what the different functions are you have in here and what they're doing. Sometimes maybe you have to look at the graph. Let me take a look at the graph of these. I made these up, so probably I can't look at the graph. But let me bring up my magnifier. And hopefully I'll be able to do this. Yeah, this may not come out very well. There. Okay. I'm choosing window, and I'm choosing 3 dimensions. Now you need to look up above. I'm trying to make that a little bit bigger so you can see it. It's still not very big though, is it? Oh, I meant that to be 200%. Okay. So go to window, and I'm going to choose 3 dimensions. And there we go. So I'll come up here, choose equation. I'll probably just do one of these to show you how to plug it in. And of course it's popping up with the menu down there, which I don't want, but now choose equation, and you see there's different ones here, parametric, implicit. I'm gonna choose implicit. That's just not gonna work. I just don't got enough screen space for that. Well, ignore that. I'll just have to describe to you then. Okay. Let me start over so you can see it. Do window, 3 dimensions. Equation. The magnifier works a lot better at my work. I don't know what I'm doing wrong here. It's a simple tool, so that's sorry I said something about me. Choose equation, and I'll choose implicit. And I know you can't see this, but and we got xz to the fourth. So let me do x, and then I'll do z caret 4 plus natural log, and then I'll do beginning parentheses x, closing parentheses, minus xy is equal to 3. And I'll choose OK. And then I'll choose OK again. Now choose up here, do view, axes. And over here I'll choose levels, and I'll choose auto. And then I'll click keep changes. And when I get to this point, sometimes I can use my arrow keys and rotate fairly well, sometimes not. There's our graph. And if I rotate it right here, this may be the best place to see it. See up here, these z values are the same, aren't they? And then, but if I pick a point over here or a point over here, they're going to have two different x, y values. So that's why this one here, that's why this one here was not a function. So again, if your tool's halfway decent, this is a free one. This is WinPlot. Then you can look at it and kind of see it. WinPlot does not always give us the best graph, though, so you can't rely on that. Now, again, there are more expensive ones you can buy, but free is in my price range. So, sorry about magnifier. I thought I could get that to show, but I was playing with it before I started the video, believe it or not. But it must not have been doing 3 dimensions. Let's see. Let's take a look at this function. fxy, f of xy is equal to x squared y minus 3x. And it says find and simplify the function values. This is just evaluating a function. So we want to plug in 4 for x and 2 for y. So for a, we're going to find f of 4, 2. So just wherever you have an x, you'll, well, let me go ahead and put my parentheses in first. Remember, evaluating a function, your first step was to go through and replace all of your variables with parentheses. Now we're going to plug this in for x, and we'll plug this in for y. So we got 4 here, and y is 2. 4 squared is 16 times 2, minus 3 times 4 is 12. So that gives us 32 minus 12, or gives us 20. Now for b, f of 1, negative 2. So again, we're going to plug this in for x, plug this in for y. So good idea to go through and replace all of the variables with parentheses first. And then we'll put 1 in for the x, and we'll put negative 2 in for the y. 1 squared is 1, times negative 2 is negative 2. Negative 3 times 1 is negative 3, which then gives us negative 5. And then part C, we want to find f of 0t. So again, we'll go through and replace our variables with parentheses. And this is our x and this is our y, so we'll put 0 in for x. And we'll put t in for y. Well, 0 squared is 0, times t is 0, minus 3 times 0 is 0, so 0 minus 0 just gives us 0. That wasn't a very exciting one. And let me save that page. I think this is functions of several variables. Functions of several variables. Page 01.pdf. There we go. And let's look at our second problem on that. Got f of xyz. Here we're throwing a fourth dimension in. Is equal to 3xy over z. And we want to find f of 1, negative 3, and 4. Again, just the variables you have right here, that's what's going to tell us plug in what where. This is x, this is y, and this is z. So, for the x, we'll put a 1 in. For the y, we'll put a negative 3 in. And for the z, we'll plug in a 4. 3 times 1 is 3, times negative 3 is negative 9. So we end up with negative 9/4. B, we want to find f of 0, 2, 5. So again, where x is, we put in 0. Where our y is, we put in 2. And where our z is, we put in 5. Well, 3 times 0 is 0, times 2 is 0. 0 divided by 5 is 0. So that gives us 0. And for C, we want to find f of 1, 2, 12. Again, what I'm doing is, I'm going through and putting parentheses over where I have a variable, and then just plugging in. This is our x, this is our y, and this is our z. So 1 in for x, 2 in for y, and 12 in for z. And 3 times 1 is 3, times 2 is 6, so 6/12 reduces to 1/2. And those are our answers. Okay. Take a look at our fifth example. I got f x, y, z is equal to square root of x minus y minus z. And our first one, we want to find f of 12, 2, 1. Well, again, we're just going to go through and where x is. This is our x, this is our y, and this is our z. So plug 12 in for the x, minus y is 2, minus z, which is 1. 12 minus 2 is 10, minus 1 is 9, so we got square root of 9, which gives us 3. B, we want to find f of 5, negative 10, and negative 10. So we're going to go through. And again, if you mess up on signs, it's probably a good idea for you to go through and put parentheses in before you plug in your numbers. Everything else remains the same. And this is x, this is y, and this is z. So x we said was 5, y is negative 10, and z is negative 10. Negative negative becomes positive, so we got 5 plus 10, which gives us square root of 25, which gives us 5. And C, I want to find f of 871. 871. So we're going to have 8 minus 7 minus 1. 8 minus 7 is 1. 1 minus 1 is 0. So we've got square root of 0, which gives us 0. And let me save that page. Oops. Let's look at our next one. Got f of xy equals 3x squared plus y. Now remember, this is interchangeable. When you got this 3 dimensions here, that's interchangeable with z. So this is the same as, writing it as z is equal to 3x squared plus y. Now this is very handy if you're graphing it, if you're plugging it into WinPlot. This is handy here if you're doing what we're doing, evaluating. Okay, so A. We want to find f of x plus delta x, comma y, minus f of xy all over delta x. Excuse me. Well, we got f of xy, so that's good. We just need to find this first part here. So first, we want to find f of x plus delta x, comma y. So we're going to go through, and everywhere we have a variable, we'll put in parentheses. So everything else remains exactly as is. Now this is f of xy, so we're going to plug this in for the x, where the x was, and we'll plug this in where the y was. So I'll put in x plus delta x right here, and I'll put in y here. Well, x plus delta x squared means x plus delta x times x plus delta x plus y, which gives us 3 times x squared plus x delta x plus x delta x plus delta x squared plus y, which gives us 3 times x squared plus, since these are the same, that gives us 2x delta x plus delta x squared plus y. And then I'll multiply the 3 through. So I got 3x squared plus 6x delta x plus 3 times delta x squared plus y. Now we're ready to plug it in our formula. So our formula says that we want to find this. So f of x plus delta x y minus f of x y over delta x. Well, this is our f of x plus delta x y, so we're going to put in 3x squared plus 6x delta x plus 3 delta x squared plus y minus f of xy, which was 3x squared plus y. And I'll put parentheses around it because that minus has to flip the sign of both of those, over delta x. This formula probably looks familiar if you've worked with the limit definition before for the derivative. Negative out in front of the parentheses flips the sign of everything inside, of course. So this becomes 3x squared plus 6x delta x plus 3 delta x squared minus 3x squared minus y all over delta x. Now we want to cancel what they have in common. Here's 3x squared minus 3x squared. Those are going to drop away. And I dropped my y here, didn't I? I got a plus y I'm missing. Okay, let's try that again. Okay, plus y, and then minus 3x squared minus y. I was wondering where that went to. Okay, we already said the 3x squareds drop away. Well, here we got a plus y, here's a minus y, so those are going to drop away. So let's see what that leaves us. Let's see, we're going to have 6x delta x plus 3 delta x squared. I guess that's the only thing left up on top. Now you notice up on top everything has a delta x, so I'll factor that out. So I'll bring out a delta x, and that leaves us 6x there, plus 3 times delta x over delta x. Well, now everything's multiplication up on top here, so the delta x's will cancel. You can only do that when you got multiplication, this times this. And that leaves us 6x plus 3 delta x. That's our answer. And this, see how we had these in for the x's? If we were to take that one step further and plug 0 in for delta x, this would drop away and we'd be left with 6x. Well, think of it if I ignored the y and just took the derivative with respect to x. This would become 6x, wouldn't it? So we'll talk more about that later on, but it doesn't look like I have room for the second part on here, so let me do that on the next page. When I say later on, I'm talking about a different lesson. Okay. Okay, so part B, we got number 6 is equal to f of xy is equal to 3x squared plus y. Okay, and then B, we want to find f of x y plus delta y minus f of xy over delta y. Okay, so first thing, just like before, we need to find this f of x y plus delta y. We're going to go through our original function, and again, where your variables are, you're going to put in parentheses. This one's easier. This is going to replace where our x was, and this will replace where our y was. So x just remains x. That's not very exciting. But the y, in our original function becomes y plus delta y, which gives us 3x squared plus y plus delta y. Okay, and then second, we're ready to plug it into our formula. So we got f of x y plus delta y minus f of xy over delta y. And we just said this first part here is equal to this, so that's 3x squared plus y plus delta y minus f of xy, and again I'm going to put parentheses around it because that minus has to affect everything, over delta y. Well, negative in front of our parentheses flips the sign of everything inside, so we got 3x squared plus y plus delta y minus 3x squared minus y over delta y. Combine together like terms. 3x squared minus 3x squared drops away. Y minus y drops away. So up on top we're left with delta y, and on the bottom we're left with delta y, which just gives us 1. And if you think about it, if I were taking derivative of this just with the y's and ignored this, derivative of y is 1, so it makes sense. Now there's no delta y's left, so if we think how our limit definition went, we wouldn't need to plug 0 in for delta y, because there isn't any. The next problems talk about the domain and range. Now we're not going to focus so much on the range as we are the domain, so that's mainly what we'll take a look at. We'll talk a little bit about the range, but if you remember about your domain, we had some different items we need to worry about. If we have fractions, then there's to be no zeros in the denominator. So you can't have a denominator equal to 0. If we have a radical with an even index, then what's inside's got to be positive. So no negatives inside the radical. So no negative inside radical. If we have a log of some form, well, then we can't have a no log of 0 or a negative number. And we had other items we needed to worry about. We had piecewise functions were a different beast altogether, but we also had trig. We had tangent, cotangent, cosecant, and secant. But remember, all those could be written in fraction form, and they go back to this one right up here. So for our domain, we're just looking for the items that we cannot have, and that helps us to figure out what our domain is. If you don't have any of the bad items, no fractions, no radicals, no logs, no trig, so forth, then by default it's all real numbers. So let's look at our first one here. So we've got f of xy is equal to 4x squared minus y. Now if I think what are possible values I can put in for xy? Well, there's no fractions here, there's no radicals, no logs, no trig functions. Everything's a nice polynomial. Which implies I can put anything in there. So for our domain, you could write the domain is a set of all xy values, our points, such that, so the vertical bar here, such that x is any real number, and y is any real number. Now domain is the more important one, and range is the harder one to find, because range is driven by the domain. So Usually domain is what tells us what are the acceptable values you can put in there. And then the z doesn't have any choice, it just follows. Well, if I were to put in 1 here, for example, for the x and 1 for the y, well, I'd get 4 times 1 minus 1, which is 3. I could put in negative values. I could put 0 in for x, and I could put negative 5 in here. And we'd get 0 minus a negative 5 gives us 0 plus 5, or 5. Now I could put 10 in here for the y, and I could put 0 here, and we get a negative value. So it appears like for our range, our z value can be anything. So different ways you can write that. Since I'm being lazy, I'll just say negative infinity, positive infinity. Let me save that page. Time for my tablet to blow up, so we'll bring up another one, and we'll look at the next problem. F of xy equals 7xy x minus 3y. Now, back in every math class up to now, actually, let me grab a drink here. No. Every math class we've had up to now, which said the domain is your x values, the range is your y values. They may have indicated it can be more than that, but that's what everything focused on. Well, realize your domain is what values can you put in over here. These are your independent variables. You can plug anything in for them. And then this is our dependent. So whatever you plug in here drives this. This is our range. So because it's kind of different. Our domain is going to be what x, y values can you plug in. We're talking about points. Well, we got a fraction here, so we got a problem. We can't have the denominator equal to 0. So let's set it equal to 0. So we got x minus 3y is equal to 0. And different ways you can do this. Probably the easiest is just take the negative 3y over, and you get positive 3y. You could also take that over and then divide both sides by 3 and put it in terms of y. You know, probably depend upon the book and what form they put it in. So our domain will be the set of all x, y values such that x cannot equal to 3y. Because if x is equal to 3y, that means you got a 0 in the denominator. So there's actually an infinite number here of problem areas. Not just one value, but there's an infinite number of points that causes us problems. So that's our domain. Excuse me. Now our range is not so easy to think about. Definitely I could put in different combinations of positive and negative for the x and y. And then it would give me all my positive and negative values. If I put 0 here and 0 here, think what that that's the only way you can get z equals 0, by the way. So if I put 0 here and 0 here, that'd give me a 0 up here, which would give me z is equal to 0. But if I put 0, 0 here, then I would get 0 minus 3 times 0, which is 0, and you can't have that in the denominator. So our graph doesn't exist there, which implies z cannot equal to 0. So for our range, again, I could put it in different forms. I could, put it here z such that z cannot equal to 0. Now I'm curious if our graph would actually show this on WinPlot. Again, that's one of them you have to kind of think about. Range isn't so easy. Sometimes I have trouble thinking them through. And I know this is small, you can't really see it, but what I'm doing, I'm clicking Window, choosing 3 dimensions. I'm choosing Equation. I'm choosing actually I could choose explicit on this one, but let me choose implicit because I figured out how to graph 3D on this package, and I'm so excited about it. So say z equals, and we got 7xy up on top, so I'm going to put parentheses around it. So do a beginning parentheses, 7xy, closing parentheses, divided by, beginning parentheses around the bottom, and we got x minus 3y in closing parentheses. And then I'll click OK. And I'll click OK again. Now choose View, and then I'll choose Axes, and then Axes. And I'll come over here to Levels, and choose Auto, and then I'll choose Keep Changes. And try to rotate it here. And it's thinking. Well, anyway, you see how this kind of curves in like this, and then over here curves like this? Well, I'm just, if I could rotate it, I could show it to you, that it doesn't exist at x equals 0 and y is equal to 0. But I can't seem to rotate it, so you just have to take my word for it. Either that or go to a good graphing package. I'm still figuring out how to graph 3D and on some of my graphing calculators, so hopefully in the future I'll be able to recreate the video and have a little bit better view of that. But anyway, that's our domain and range. Okay, let's look at this one. F of xy is equal to square root of 1 minus x squared minus y squared. Well, here we have a radical with an even index. So I'm going to take what's underneath there. So we've got 1 minus x squared minus y squared. And this cannot be negative, so we want that to be greater than or equal to 0. Now I'm going to take the negative x squared, negative y squared to the right side. So we've got 1 is greater than or equal to x squared plus y squared. And if I flip those around, we've got x squared plus y squared is less than or equal to 1. Now if I think about x squared plus y squared equals 1, I know this says less than or equal to 1, but if I just think about the equal to 1, well, that'd be a sphere, or not, I mean a circle, and it would be radius 1. So it'd go like this if I look at just the x, y values. When I say less than 0, well, then it keeps coming in. So, you know, you got circles coming in. Infinite number of circles coming in, actually. Use your imagination on the picture of that. Which implies that all my x, y values in here are in my domain. Because we found what we can have. We set it greater than or equal to 0. So for our domain, it's going to be the set of x, y values such that x squared plus y squared is less than or equal to 1. Now for our z values, our range. Now I'm actually going to write z here instead of the f of xy. Set of all z values such that z, now can it be equal to 0? Well, we said less than or equal to 1. 0 is a possibility, isn't it? So if I put 0 here, that'd be a possibility for what this is saying. But if I put 0, if I go back up to here, let me graph it. Maybe that'd be better to show. And I'm going to just choose window, and I'm going to choose 3 dimensions. And you may have better luck with choosing equation explicit on these. Because if it's already solved for z, you can plug it into here. And I'm going to plug in square root of 1 minus x squared, so x caret 2 minus y caret 2, closing parentheses. And then click OK. Now, unfortunately, that plane is not supposed to be there, but remember how I was talking about it as a sphere? Well, it's half a sphere, actually, because you have z is equal to the square root, and square root can't give you a negative value. Now, the question is, can you give you a 0? And that's what I was trying to indicate down here. Well, if I put 0 here and 0 here, that has nothing to do with whether z can be 0. But if I put 1 in for x and 0 in for y, Well, that'd be 1 squared, and 1 minus 1 is 0. So it can be equal to 0. So we're going to have the range is a set of all z values such that z is greater than or equal to 0, like that. Let's take a look at this one. This one wants us to sketch it. And I'm not going to actually sketch it. I'm going to plug it into my utility here, and we'll take a look at it. So I got 2 plus 3x minus y. Think about what this would look like, though. Everything's the first power, isn't it? If I were to replace the f of xy with z, you got z is equal to 2 plus 3x minus y. Everything in first power implies it's going to be a plane. Let's go look. Excuse me. I'm going to close that. Now choose window, choose 3 dimensions, equation, explicit, and this problem is 2 plus 3x minus y. So 2 plus 3x minus y, and then I'll click OK. And choose view, axes, and it'll let me rotate it better in explicit view. And you see it is indeed a plane. Now this graph looks like it just stops here, but it keeps going forever in all those directions. So, and for the homework, I just want you to sketch that down as best as you can. Do not spend a lot of effort onto it. Now, if you're going to use this utility, there's even an easier way. You can do a file, bitmap to clipboard, and then go into Word and just paste it, and then turn that in. Okay, so let's look at our next one. Got f of xy is equal to 3 times square root of x squared plus y squared. And sometimes you can look at this and kind of figure out what this graph is going to kind of give you an idea of. You know, z can't be negative, can it? Because square root always gives you a positive number, and then 3 times that is going to be positive. And if I think about what x squared plus y squared entails, this part right here has got to be positive or is equal to 0. So we're going to have x squared plus y squared is greater than or equal to 0. So let's take a look at it. Choose window, 2 dimensions. Now choose equation, explicit. And this one was 3 square root of x caret 2 plus y caret 2. And then I'll click OK. What did I choose? 2 dimensions? Let me close that. Choose window, 3 dimensions, sorry. And then choose equation, explicit. And 3 square root of x caret 2 plus y caret 2. Click OK. And now do view, axes. Looks like that. Okay. I talked about this, the x squared plus y squared has got to be greater than or equal to 0. It can be equal to 0, which if it's equal to 0, it means that it's a point. So if I look down here, rotate it a little bit. So I start rotating it. You can kind of see a circular pattern there until it becomes a square. So it's a circular pattern. So it begins at a point. Well, then as it goes up, and if I put 1 here and 1 here, this is a circle, and so it becomes a circular pattern, and you can kind of see that. You know, as you rotate it, and you're kind of getting a good feel for it, it makes sense why it's a circular pattern. Don't ask me why they give you a square up there at the top. But there is a circular pattern there, especially if I rotate it. It's like, okay, that's obviously a circle. Which we know that from what x squared plus y squared looks like. Anyway, To export it, do like I showed you. If you want to sketch it, that's fantastic. Let's take a look at this one. Understanding a little bit about what your domain is helps you to interpret your graphing utility, see if it's giving you something correct, if you got a cheap one like I'm using. Now, e to the x, you notice there is no y here, which means y can be anything. So that'll help us to figure out what this graph looks like. I'm going to close that. And I'll choose window, 3 dimensions, and I'll choose equation, explicit. And this is, what is this? E to the x. So I'm going to type exp, beginning parentheses x, closing parentheses. And let me get that magnifier going, see if I can give one more try. Magnifier, except for ease of access. Magnifier. There, you see it. So what I'm putting in z is equal to exp, and then beginning parentheses x, closing parentheses. Hopefully you can see that. And then I'm coming down here and I'm clicking OK. And this is what my menus look like. You can at least see that. I'm choosing. Okay, well I guess you can't. If I had it up a little bit more, you probably could. But then, or not. Okay. At least you saw that one window. Okay. And make that a little bit bigger. Okay. Now if I do my view axis, put that on there. It looks like the graph of e to a power, doesn't it? Now it looks like it just stops here. It doesn't stop. It keeps going forever, just skimming that. And it doesn't just stop here. It keeps going up forever. And since our y value can be anything, it's not just stopping here and stopping here. It's going forever to the right and forever to the left when I got it facing this way. So in terms of your y direction. And again, you can just export those and get your picture. It might have. Let me save that. I'm not sure if I have room for the next problem. I encourage my students to play with WinPlot, rotate it, and so forth. By using a 3D package, you really do get a good feel for what the graph looks like. By trying to sketch it in 2 dimensions, you just don't get a very good feel for what they're referring to. But not everybody can have a computer sitting there where they can rotate it and look at it in 3 dimensions. So the problem becomes, how do you show the 3 dimensions, the height of a map when you got a two-dimensional map, for example? And that's what these next problems are referring to. It says describe the level curves of the function. Level curves help us to show the changes as the z value changes. For example, in this problem, we got z is equal to 3x plus y, and you got c is equal to -1, 0, 1, and 3. So what we do to have us to get a good feel for this is we plug in each one of these c values for the z. Because z is equal to 3x plus y, we could rewrite that as c is equal to 3x plus y. So on this one, we're going to have -1 is equal to 3x plus y. Take 3x over there, we get -3x minus 1 equals y. Now in this one, we'll plug in c is equal to 0. So we got 0 is equal to 3x plus y. Take that over. We got y is equal to -3x. And if we plug in c is equal to 1, we got 1 is equal to 3x plus y. Take that 3x over, we get -3x plus 1 is equal to y. And c is equal to 3. We get 3 is equal to 3x. What am I doing? I'm trying to get the eraser. I was thinking about something else. I was thinking about how I was going to graph these. I don't graph them real well by hand, but I could try. Because what they're indicating to us is after to describe the level curves and sketch them. It's probably easier to sketch them first, and you can probably see what's going on. But these are all lines, and they're parallel lines, which would be obvious if I graphed it well. Okay, so this is -1. And let's see, 1, 2, 3, 1. Wish this tool had a straight line tool. That'd be that one. Now this one y is equal to -3xy, which would be this one. And this one is y is equal to -3x plus 1. They're parallel lines. And I'm not drawing that real well. And this one would be +3. So it'd be something like that. Let me go over and do it on WinPlot. I can do it on the calculator though, so let me do it on the calculator. Because remember, we're trying to show the 3 dimensions in 2D. Okay, so if I press y equals, press clear, on y1, I can put my first one, which is -3x minus y. So -3x minus y. What did I say? y1. This one's -3x, so I'll down arrow to y2 and put in -3x. And of course it actually helps to graph them correctly. That should be a minus there. Go back to bed. And next one is -3x plus 1. So -3x plus 1. And then the next one is -3x plus 3. Okay, and then I'm going to press graph. Like the mistake of my graph, they were too close together, so they were starting to, that's why I had to fudge it a little bit. But on the calculator here, the neat part about TI3, TI4, you can press zoom to zoom in, number 2. Once it comes back, press enter one time. And I still not going to have all of them, I don't think. Yeah, I thought that last, well no, there's the last one. So then you can see it a little bit better. Now when you're sketching this on your paper, usually the C's are labeled. So like this one, you'd write C is equal to -1, this one C is equal to 0, this one C is equal to 1, and this one C is equal to 3. Like that. They in the textbook they have a pretty good picture of a contour map where you have heights, you know, the hills, the mountains, or whatever you're looking at, and then has the elevation right next to it. So you can see, you know, as a different as it changes, what the different heights are, which is where it's especially useful. But if you're graphing in 3D, the level curves are crucial. If you're doing it by hand, I should say, the level curves are crucial to understanding what your picture looks like. Okay. And some people do these in their head and think about it. So 2x squared plus y squared, and C is equal to 0, 1, 2, 3. Now this one I am going to do on WinPlot because it's easiest that way. So let me shut my calculator down. So C is equal to 0. I plug 0 in for the Z, so I got 0 is equal to 2x squared plus y squared. And then I also got C is equal to 1, so I got 1 is equal to 2x squared plus y squared, and C is equal to 2. And I got 2 is equal to 2x squared plus y squared, and C is equal to 3. And I got 3 is equal to 2x squared plus y squared. Now this one is a little bit tricky. I asked in class what this one looked like. I don't think anybody got this. If memory serves me right. But this form here, if I look at this one, this is an ellipse. And if I put it into the correct form, this would be x squared over 1/2 plus y squared over 1. So again, we have to write this as something squared, so this would be this would be 1/2 squared, like that, and then this would be 1 squared. 0.5 squared. I shouldn't have to come over the calculator and do that, but is that really that? I hate decimals. 5 squared is 25, so I'm assuming it's 0.25. That doesn't seem right, though. Maybe I better go back to bed. Let's see. 0.5 squared. Yeah, sure enough. Okay. Seems like I did that in class, and I did something a little bit different. But what am I putting that? I know why. It's a basic trig mistake. It's a square root of 1/2 squared. That's why. I know it didn't come out something nice. Because if to rewrite this as something squared, you can always put a square root there. Because square root and the second power cancel and just leave the original 1/2. Okay, so now the square root of 1/2. Okay, 0.7. So if I were to sketch this one, for example, and I won't sketch all of them, since this is 1, then I'll put a point there, and then I'll put a point down here on our y-axis. So 1 and -1. This was 0.7, so if this was 1 here, 0.7 might be about right there. Then over on this side be -0.7. And so it would be an ellipse, going like that. So these are a bunch of ellipses, ellipsi. But this one over here, though, this is 0. So this does not fit our form. I mean, these, well, you might say, well, that's not a 1 over there. But I could divide everything by 2. And then we'd have 1 is equal to x squared plus y squared over 2. And this would give us an ellipse. But this isn't a 1, so it's a degenerate case. This is actually a point. So this one gives us a point. Well, let me actually sketch them now on a good utility. So I'll go to WinPlot. I'm going to close this down. I wish I could magnify this so you could see it, but I'm choosing Window 2 Dimensions, and I'm choosing Equation, and I'm choosing Implicit. And our first one is 0 is equal to 2x squared plus y squared. So I'm putting in 0 equals 2x caret 2 plus y caret 2. And I'm clicking OK. Now that one's kind of boring since it was a point. The only way I can get the point there actually is do an equation, point, xy, and choose 0, 0. And I'll choose solid. And then click OK. And it puts our point there. But let me do the next one. I choose equation and choose implicit. And the next one was, I think 1 equals 2x squared plus y squared. The only thing I'm changing from the first one is I put 1 in instead of 0. And then I click OK. And if I choose equation, choose implicit, and I do 2 equals 2x squared plus y squared. OK. And then choose equation, implicit, and 3 equals 2x squared plus y squared. And click OK. And again, that gives us our graph we're looking for. Sketch of level curves. So again, you can export that. You can do a file and choose bitmap to clipboard. I wonder if I can actually paste it into here. Never have done that. I must screw up if I try to do that. I don't see a paste. So let me save this. There we go. And Now I'm going to stop the recorders. I think that was the last problem. Yeah, it was. Oops.